All right, so let's talk about the steps for solving systems with nodal analysis. As I said, we have to select a reference node. That's usually, or even often, the lowest voltage in the system or ground. And then assign node voltages. By assigning node voltages, I mean give them variable names to the remaining nodes. And then apply Kirchhoff's current law, or KCL, to each non-reference node and express the unknown currents in terms of the node voltages using Ohm's law. Ugh, that sounds like a lot of steps, but you're going to see that it's really pretty straightforward. So then you solve for the variables that you're interested in. So take a look at the resistor on the right. It's connected to two nodes, nodes A and B, that we've arbitrarily labeled. And let's just say that node A is at a higher voltage than node B. So node A is the higher voltage, node B is the lower voltage. Therefore, the current I would be flowing from A to B because it's going to flow to the lower potential. All right. So writing the currents going into node B, for example, we'd express them using Ohm's law. So this right here, express them in terms of Ohm's law, that's this, right? V higher minus V lower. So in other words, that's the differential voltage across the resistor divided by the resistance in between those two nodes is the current. So let's see how this applies, how we apply this to a circuit. Okay, so we've got the circuit on the left shown, and then it's the circuit on the right in figure B is just repeated, but it's showing some of the currents on there. Okay, so we're going to actually draw these currents here. So we've got a circuit. There's a couple of current sources in it, I1 and I2, DC current sources with capital I's, and then we're interested in the voltages V1 and V2 across R1 and R3, and a couple of nodes have been labeled for us. Node 1, which we're going to call V1, and node 2, which we're going to call V2. Okay. Now, there are some currents that are going in and out of these nodes, and we'll just label them. We'll just call this I1, the current. And I'm going to use lowercase variables here. Not that this is an AC current. I'm just using it to differentiate between the constant current sources and these branch currents. So we're going to use lowercase I here. So we've got I1, the current going through resistor 1. We've got I2, the current going through resistor 2. And I've arbitrarily drawn the direction of that. Do I know it's actually flowing in that direction? Not really, but let's just go ahead and write it that way. And then we've got I3. So let's then now do KCL at, okay, so right now I'm backing up a step, sort of. I'm showing the KCL here. When we get better at doing nodal analysis, we'll just start writing it in terms of the node equations, which you'll see is we're going to write it as like the way we saw it just a moment ago. But for starters, we'll just show KCL so that we can very clearly see what the currents are. So KCL at node 1, we've got I1 coming into the node, right? That's coming in here. A capital I1 going into the node. We've got a capital I2 going out of the node, right? So you get a minus I2. And then I1, little I1, we already drew it as leaving the node. So it's a minus. Little I2, we drew it as leaving the node. So it's a minus. And that is all the currents in and out of the junction. And that's our equation 1. Now, if you go back to the slide just before, it says Step 2, apply KCL to each non-reference node, then express the unknown currents in terms of the node voltages using Ohm's law. So that's what we need to do. These are the unknown currents, I1 and I2, right? And we now want to express those in terms of the node voltages. Okay, so we get, if we rewrite it, we get I1 minus I2 minus, okay, I1, we can write it as, well, this would be the voltage across, so V higher minus V lower, so it's V1 minus 0 divided by, well, it's R1 in this case, and then minus a V, so now we're going to do the current I2. So the current flowing through R2 is going to be the node V1 minus the node V2 divided by R2. And all of that is equal to 0. And that is our first equation. That would be equation 1. So you can see that shown in this form, if the current sources I1 and I2 and the resistors R1 and R2 are known, we have two variables that are two unknowns, V1 and V2. So we have one of the equations. Now to get the second equation, we're going to do KCL at node 2. All right, so again, remember that's this node here. We've got an I2 coming in, right? So there's I2 coming in. We've got a little I2 coming in here, plus little I2 that's entering the node. And little I3 is leaving the node. So all of that is equal to 0. Okay, if we were going to do step 2 then, we would rewrite this, we would rewrite the unknowns, the lowercase variables, in terms of the node voltages across the elements, and then be divided by the resistance in between. So I2, remember we said that that's V1 minus V2. And why is it V1 minus V2? Well, we drew the direction as flowing towards, I2 is flowing towards the right through resistor 2. So it's V1 minus V2 divided by R2 minus, and notice that I'm drawing everything in parentheses very carefully right now so that we're keeping track of the sign. I want to really emphasize that. So like, you know how the signs, these signs, the plus and minus signs were determined by whether the current was entering or leaving the node. Make sure you leave those on the outside of the parentheses for now. We'll talk about other ways to do it as we go through. But that helps us keep track of the sign. So then I3 would be, well, the voltage on one side of R3 is V2. The voltage on the other side is 0, ground. The resistance in between is R3, and all of that is equal to 0. And that is our equation 2. Two equations, two unknowns, and you can algebraically rearrange this and solve the system.